Hey everyone, welcome to the Road to Agentic AI. In this series, we break down the tech behind Agentic AI, how it's transforming work, helping scale capacity, cut down manual tasks, and how it frees up teams to focus on strategic objectives. Last time we talked about prompts and how it's not so much about telling the machine what to do, but about architecting probability space. But to fully understand agentic AI, we need to expand our understanding even further, which is why today's topic is latent space, the conceptual landscape in which meaning is formed. From here, we'll discuss how to use chain of thought, perhaps the single most powerful LLM prompting technique. Quick intro, I'm Jules, CISO at Prowse Consulting and an advocate for agentic AI. If you have questions, feel free to use the email below. But now let's get to today's topic, thinking in latent space. Welcome, everyone. We're on our third session here about working towards understanding agentic AI. And the topic for today is thinking in latent space, which is a term that might not make sense right now, but I'm sure we'll get you guys there. So to pick up from where we were, last time we focused on prompting and how prompting helps us architect probability. And we explored this idea that prompts utilize patterns, such as scenarios or personas, and we can use those to influence the probability of specific responses in ways that align with our intention. We concluded that if patterns allow us to shape probability, then how far can we take that concept? Can we include stuff like reasoning in that? So today we're going to focus on what is known as emergent behavior of large language models. All of this is still building towards having this understanding of the core functions of AI and to get us into a mindset where we can think about agentic design in a way that will help us do that. So this is probably going to be the most theory-centric one of these presentations so far. But also the last one that I think we'll have to talk about just theory for. And after this, we'll probably move more on to practical implementation because you'll have got a good baseline understanding of what we need to know to be able to approach design for agentic systems in the right way. So here we are in session 3 here, and session 4 we'll start talking about some of these topics that are probably important to you, like hallucinations, but through the lens of what we've learned so far. So here is where we are. We talked about how large language models work. We talked about the idea of breaking prompts into tokens and assigning them vectors and probabilistic calculation that happens to predict the next token, and how that's based on patterns of how tokens tend to occur in similar contexts. And then we talked about how prompting shapes probability by using larger patterns formed by co-occurrence of elements in training data. This allows us to influence things like style and format and structure. And then we talked about how far that can be taken. So if you look at both of these side by side, we're really still actually talking about the same topic. At a large scale and a small scale, we're talking about how patterns create emergent probabilistic pathways. And the whole idea of this is basically that what we're talking about today is still exactly the same topic, actually. We're still going to be talking about how patterns influence probability, but we're going to start talking about it through the lens of this concept of latent space. Let's talk about what latent space is. This term basically is constructed from these two words, and latent means something that's present but not visible or apparent. You might have heard that in expressions like latent talent, like things that feel like they're tangibly there, but you can't quite put your finger on where. And space in this case is referring to the spatial relationship between points in multidimensional space. So it's a sort of abstract geometric construct that's unseen to us. And this unseen, inaccessible, internal, multi-dimensional geometry is what a model uses to make these relationships, to draw relationships between how words, concepts, and phrases are connected. In fact, if you remember the first presentation, we talked about this by showing a one-dimensional graph, a two-dimensional graph, and a three-dimensional graph. That is basically latent space if you scale it up to the 1500 plus dimensions that current models use. That's what that is. Why do we need to know about this? Understanding this concept isn't really just a little thing to know about how they work. It's really the lens through which you can understand what LLMs can do at all, how they can function at all. The thing is that once you start thinking this way, you realize that large language models don't actually perform tasks. They're just completing patterns. So every kind of output that you get, whether it's translating or reasoning or planning or design, they're all just these patterns being traced by a probabilistic system. And the reason that prompting works is that basically your prompt isn't instructions. It's you intentionally positioning the model in a very specific region of latent space to output things that are aligned with your goal. Reasoning emerges because you're telling it, I want you to think like this way that you've seen before. In the same way as a normal prompt puts the right words, puts it in the right space and latent space to output the right words, on a larger scale, you can trace a pattern of something that resembles logic by using the right phrases. And the reason that all these things can be combined and that LLMs can do so many things is simply because of this ability to mimic pattern. So it changes kind of the way that you interact from this concept of what prompt gets the result that I want to what kind of structure, what kind of pattern am I asking the model to trace here? That can be tricky. That what we were just talking about, and the reason that that question came up is because it's very difficult to conceptualize of this. So let's have a look at an example that might help us reframe our intuition here. As a human, if you imagine translating a sentence from English to Spanish, your reasoning might feel something like you read the words, and that gets translated internally into some kind of meaning, some sort of concept inside your head. And then you take that concept and you rebuild it in Spanish, okay? That's what it might look like roughly. It's a cognitive process. It depends on comprehension and understanding intent. We think and then we express our thought. We're not just swapping words out. We're actually reconstructing meaning. We're taking this concept and rebuilding it in a different way. So when you see a large language model translating text for you, it can be very difficult to think about this happening without any comprehension at all. But we already know that isn't how they work. They always work in the same way. Take the prompt, convert it into tokens, calculate the probability of the next token, and then output that. As these tasks get more complex, and they're things that like moving from one whole language to another while maintaining the meaning of the sentence, it feels like it's difficult to conceive that this is happening just based on probability. The thing you have to understand is this is the critical point you have to understand is that in traditional software, like we're used to, if you use something like Microsoft Word, features get implemented explicitly. Someone says, users should be able to make text bold. So a software engineer implements a system for that to be possible. They code it by hand, they think through the logic manually, and that feature is then implemented into the program. Large language models are different. They're not actually programmed to do anything at all. They're just given training data and training instructions. That means that translation and summarization and reasoning, they're all capabilities that weren't added as features. They emerged from statistical relationships in the training data. So it's important to realize that this is why they behave so differently, right? Traditional software is very prescriptively designed, implemented with logic line by line. Each feature is decided on. The behavior is tested to perform the way that it should. It's designed to produce predictable, consistent output. But we're looking at a system now where there aren't any explicit feature definitions. It's not actually designed to do anything in particular other than find patterns in training data and produce output that correlates with co-occurrence of patterns in that training data. So any behavior that comes out of a large language model is just a consequence of what it was trained on. If those patterns exist in the training data, then it has the capability, based on how that pattern looks, to replicate or mimic that behavior. Let's return to for a moment here of how this actually looks like under the hood, just so we can fully grasp what just how different it is from conventional software and just what we're looking at. A visualization that I like to imagine is if you imagine latent space where all the tokens and all the vectors are housed as a sort of cloud. And you're looking at this cloud from an angle, a specific angle. You're just looking up at this cloud. And you're focused on one point in the cloud, and this point is the word cat. From the angle that you're looking at, you might imagine that it's sort of an English language centric angle. And around that point, you notice that there are other tokens like these words, like kitten and fur and meow and dog. These are things that feel close to the idea of cat if you view it through an English language lens. But then imagine that you could zoom around and you're now looking at this same cloud, the same point, cat, from a slightly different angle. And you'll notice that the things that you see around it from this angle are other words for cat in different languages. Maybe it's mashka, maybe it's gato, maybe it's neko. They're all words that have a very close relationship to this token when you view them through this angle. And then again, you could maybe imagine zooming around and you're seeing the same point again, but from a different angle. This time, it's a sort of a symbolic representation. It might involve hashtags, it might involve variable definitions, it might involve emoji. These things still have a relationship, but they're viewed from a different lens, through a different dimension. Now, I'm using these labels, but as we talked about in the first session, there is no way of knowing what labels an LLM uses. It decides on them based on probability. They don't have neat labels like the ones we've put here. But what you have to understand is that for every point in this cloud, there are 1,500 or more different angles from viewing it from that form the complicated geometry of how these tokens are related. This is the only thing inside an LLM, right? There's no rules. There's no grammar that describes how English works. It's just a lattice of these interconnected points with these different dimensions. There's no features inside it. It's just this data. And so everything that you see is just based on the fact that if you line everything up that way, the patterns that came from the data tend to organically converge inside that data structure. If everything is token prediction, let's dial it back to what we've seen so far. We start with something that resembles autocorrect. We can say, where did the cat sit? And we get a result like the cat sat on the mat. That's just because that pattern of how that's said has existed before. It's a very predictable way of that text being continued. But other patterns that are a little more complex, like question and answer pairs, follow the same principle. What is the capital of Paris is likely to be followed, no matter how you word this question. If it's still asking the same kind of thing, you're likely to get capital of Paris, capital of France, sorry. Capital of France is going to be Paris. And then we have writing structures and styles. On a larger scale, we're seeing that given a particular collection of words, probability will pull it towards all of the things that output being in that similar style. And then all the way up to coding and high structured writing forms, and even spoken and written language. These are all patterns. If you zoom out far enough, they're all ways in which probability will lead output into a shape that looks like these things when they've been used continuously. And so, as I said, in latent space, patterns like these cluster together organically, and any orderly seen output is just a consequence of that organic clustering. So that's why, even if we have a very high meta concept like reasoning, it's possible for it to be simulated in this way. And if you think about reasoning, it's actually it is a pattern that you see very, very often. Some examples of where you might see that are things like math tutoring and problem solving or essays, online forums, lectures or Socratic dialogue, formalized debate, logical puzzle solving, instructional tests, reflective dialogues. All of these things include the pattern of how logical reasoning is expressed by people, right? So in other words, they're examples of where in the vast quantity of training data that we have, the shape of what you need to do for reasoning to emerge is sort of present in all of these different examples, in all these different contexts, and using different words, yes, using different ideas, yes, but all tracing the same path of how you get to a conclusion. And so this architecture of abstraction is performed continuously by us, right? Reasoning isn't a function. It's a form. It's basically a way of human expression in this way. And if you, and like with all of the other things that the LLM can do, this is no different. So how can we actually utilize this? there's a prompting technique called chain of thought, which some argue is the most powerful prompting technique that you have available to you. It refers to basically any prompt which invokes patterns of reasoning to generate output. More commonly than not, this means using phrases that imitate how people express thought, something like step by step or thinking things through. It's interesting because what this gives us is something that's quite different than what we've explored so far. It gives us a way to intentionally, on the one hand, intentionally invoke simulated reasoning process, but also for that to be outputted so that we can see that. It makes the process transparent, interpretable, and subject to our own oversight. We can decide if we agree or disagree with the path that's being followed. And so the way that I like to talk about this is that it gives us the ability to audit the shape of thought rather than to just accept an answer that doesn't make sense to us. And this will be important when we go into the next session as well, where we talk about troubleshooting. So I want you to sort of think about this pattern for a second here. You've probably in your life experienced a dialogue a little bit like this one that I've got here between a teacher and a student. And just to sort of illustrate that, if you substitute the concepts that we have in this dialogue here about gravity for other things, you can see how there's sort of a pattern that's emerging here between concepts being gently introduced and continued by the student in this example. This is precisely how chain of thought works in a text prediction model, right? It's not about knowing the answer. It doesn't know the answer. It doesn't know anything. All it knows is that you can predict words on this kind of path. That's a pattern that exists. And that if you ask a question or a prompt that pulls the probability in latent space into this region, you're going to get output that looks like this pattern that it's seen before. In other words, this is basically a style. I think it's helpful to think of that as just a trail of cues. And if you guide it into the beginning of that trail, it's likely, because of the momentum of that probability, to continue down that same path. So I'm going to try to, this is actually a fairly difficult thing to show good examples for, I think, because you really have to use it and see it to get what's going on. But I've come up with an example that I think might be helpful. I've made some fictional meeting notes for this meeting here, and it's not super important that you read all of them. Feel free to scan through them. They probably look like meeting notes that you've seen before in your own experiences. The idea here is that we have a meeting that's taken place, which features multiple contradictions, conflicts, and tensions. And it can be very difficult and frustrating when you leave a meeting like that because you don't know who's responsible for doing what or what even needs to be done. So some of you may have even taken the approach of taking the meeting minutes that you've created and pasting them into something like Copilot or ChatGPT and being like, okay, summarize these meeting minutes into action items, including contradictions and interdependencies. Not a bad prompt. And no matter what the minutes are, you know that it's going to output some action items for you. You've already basically, based on what you guys know already, you know that it's going to output this because we've given it a structure. Okay. The interesting thing is, what are we really going to get out of this result? I think that this is given a decent summary of points that happen, and it did capture some key tensions and takeaways, but these action items aren't really useful to act on. I don't really consider the larger picture. It hasn't been thought through. So if I take the same prompt into Copilot and just change it slightly and say something like, summarize the meeting minutes, thinking it through step by step, and highlighting contradictions, generating a list of action items and interdependencies, basically the same prompt, but I've just put this little keyword in here. We're going to invoke the capability of simulated reasoning to come out in the response. And the response was truly quite long. I would say probably about 3 pages of text. But it included some interesting artifacts like this table here, the action items and interdependencies table, as well as this specific list of contradictions and ambiguities. And it did a much better job, a really quite an interesting job of taking the conflicts in that and trying to synthesize new action items that weren't stated in the meeting that would help resolve where those conflicts existed. And the reason it was able to do that is because of following through, writing out all of the like, okay, if that's that, then we need to do this instead, following that pattern that we were talking about earlier. And it was interesting that it even came up with a couple of things that were follow-on risks that could happen because of things that were unspoken in the meeting. We won't go into specific details of that, but basically, I hope that you can see that even just by slightly changing the way that you ask for output to express that you want reasoning to occur and you want to see it, you get a very different result. This type of reasoning has obviously, I mean, it's quite easy to see how that's useful enough that it might be useful to have in every prompt that you do. And there are some cases where that's not the case. But since it was discovered that this technique is very useful, it's actually sort of become a major feature of most large language model platforms. Even basic prompts tend to include at least some level of reasoning that you're not going to be able to see behind the scenes happening before output is generated. But even Copilot, which all of us in this organization have access to, you might not have tried clicking this think deeper option before. If you're typing in a prompt into Copilot and you just click this button, you'll get this small menu. Even if you just click this button and you don't even reword your prompt, you'll get more reasoning included in what happens in the output. So that's something that you guys, if you haven't used it before, you can just try that and see what kind of different results you get. But the thing I want to highlight is that although features like that are interesting and cool, you can do all of this without that. You can influence how you write your prompts even without these features, and depending on what language you include, you will definitely influence the kind of result that you get. All you have to do is include phrases that emphasize these patterns of problem solving that we're all familiar with, that we use in our daily lives all the time, thinking it through step by step, writing each step in detail as part of a response. You can even say use COT to solve the problem. That's a term that now exists in common parlance, and at least for LLMs, and it will be able to give you sort of ordered step-by-step reasoning in the output, or things like respond with procedural instructions and include an explanation for each step. All these things are things that you can sort of quite intuitively imagine should generate a detailed response, right? They should give you that they should require it to trace that pattern of going through the act of outputting, probabilistically outputting words that follow that trajectory of reasoning that we're familiar with. Good places to use this are in symbolic or structured reasoning tasks. I've got a couple of examples for each of these things here, like policy adherence or contract clause validation. In programming context, it can be things like API authentication, logic validation. So anything where you have to do something that requires structured reasoning. So then there's also things like multi-step context modeling. Things like if you have a business process or like a sales pipeline or something, and you feel like some parts of it breaking down, it's really good to use this kind of reasoning to work through that and try to figure out why something isn't performing logically the way that you want. Or if you have something that has multiple factors going into it and you want to evaluate how those factors interact, kind of like the meeting that I was talking about, that's another good one, good area to use that in. And also ambiguity interpretation or hypothesis generation is a really good one too. If you have something that you feel like there's a sort of a latent message in it, some intent, then it can be really good to try to draw the extra meaning in something that might be hidden out of it. I want to pause for a second here and just state that we started this particular session with talking about latent space and how understanding that is so important, and that we talked a little bit about the internal geometry of how large language models work. And the most important thing that I want you to take away from that isn't a specific understanding of how that works, but rather that it's very important to understand that it isn't one of two things. Large language models aren't magic to start with. There is an order to how they work. And secondly, that they haven't been designed intentionally to do the things that they want. They are probability machines that are based on latent patterns in training data. So understanding latent space is really just understanding that it's not those two things and that it's really complicated relational math instead. Once you see that everything is really just based around these patterns, you don't really need to understand why each of those individual behaviors works the way it does. You just have to understand that they're basically all some kind of probabilistic pattern completion, autocorrect, translation, reasoning, planning. They're all basically doing the same thing. So what we kind of get left with here is this idea that given enough attempts, given enough examples, these kind of concepts sort of form organically. Information starts to order itself. And the LLMs are just a way that we've devised of encoding these patterns into latent space. We now have a way of pushing tokens into a machine that produces probability on patterns that are on the small scale and also all the way up to very large scales. And we can use them in combinations that we couldn't conventionally. As long as you understand that, then I think that the first 3 sessions have all built up to just being comfortable with the idea. Because everything that we're going to build later, and when we talk about agentic systems, is still based on this simple principle, right? Basically, we're looking for patterns, and we're looking for pushing patterns into this probability machine so we can get results that we want out of it. So today we discussed a couple of things. We talked about latent space and how understanding that means understanding what LLMs really are. And the way that I just described, they're not tools with features, but compressed geometries of pattern. Therefore, translation and other capabilities of large language models are emergent properties of patterns expressed through the underlying data. And one very useful emergent capability is chain of thought, which we can access by prompting intentionally to invoke patterns of things. Before we move on, every AI system, no matter how complex, still involves basically the same thing, probability design. That's what we're doing. The same principles that we use in all of these things that I'm telling you about how to prompt in chat are actually the same skills and the same concepts which are used even in multiple agent semi-autonomous systems that are, self-improving, all these fancy things you hear about for the future. All of them are based on the same things that we're learning here. The stuff that you use to prompt Copilot to get a better response is the same skill, the same knowledge that is needed by people to architect complex agentic AI. It's just basically a different version of the same thing. And as we get into describing how agentic systems work, you'll see that everything is based on these same foundations. So congratulations in getting through the theory-heavy part of this set of sessions. From now on, we're going to focus on more tactical things and more practical and tangible ways in which that affects how we use AI. The next session is going to focus on the things that LLMs are quite bad at doing, how to avoid hallucinations, how to troubleshoot bad output, and how we can explain that, how we can see how to troubleshoot that based on what we know, but maybe how we can infer what else will be difficult for them to do. So thanks again. I know that was a lot to pack into half an hour as usual. Thanks very much to everyone for tuning in. I'll talk to you next time. Thanks again for joining us on the road to agentic AI. I hope you found today's insights helpful. Next session, we're going to look at the challenges we face when using large language models, focusing on hallucinations. Check your inbox for upcoming episodes and feel free to reach out with questions or feedback. Cheers.